Hello all, welcome to part 17 of the Wireless LAN Security Mega Primer. So in this video, we will actually learn about how the Cafe Latte attack works and conduct it as well. So in the previous video, we had seen that we were able to lure a client to connect to our fake access point even though we were unaware of the web key of the network the client had in its preferred network list. So what's up next? Basically what happens is after the client associates with our access point, the next logical step is depending on the IP address configuration, the client would either assume an static IP address or a DHCP based IP address. Now the most common case is DHCP. The Cafe Latte attack works for all cases, DHCP and static. In this video, we'll specifically concentrate on DHCP because that is what is more likely. So what is going to happen? In a previous video, as we saw, the client will start making these DHCP requests, but unfortunately, because we have a fake access point, nobody is going to answer to that DHCP request. So eventually DHCP will time out, and once DHCP times out, the client will assume a auto configuration IP address in the 169.xxx range. And basically what happens after that is it will send out gratuitous R packets announcing the IP address. Now we've seen this in a previous video, but let's very quickly verify this condition. So let's go to our hacker machine and let's actually start Airbase NG with the PON.me network. This is the exact configuration which we used in the previous video, right? And here let's quickly start sniffing for the PON.me network. So let me go ahead and add this to be the BSSID filter. And as always, all we are interested in are the data frames. So let me go ahead and add a filter for data. And let me start the sniffing once again. So now let's go back, and now what we'll do is our client, which is currently sleeping, will be rudely woken up to connect to our Wi-Fi network. So I'm switching on the Wi-Fi on my iPhone, and you will notice that it will connect to the pre-configured web network, which is PON.me, as you can clearly see. And on the screen, you're able to see that the connection has actually happened. Now let's go back here and see what we found. Interestingly, if you notice, we are seeing the DHCP packets which the client is sending. Eventually it times out. Now let's kind of stop this. I think we've gotten what packets we wanted. And if you notice, eventually it times out, and so let's just concentrate on the ARP packets. Let me add a further filter for ARP. Right, so eventually the client decides to take up an auto configuration IP address because it did not get a DHCP based address, and then it sends out these gratuitous R packets to announce it. Now, one very important thing you need to note: the attacker cannot see any of these packets in plain text simply because he does not have the web key. The reason I'm showing you the decrypted packets after applying the key here is so that we can understand this situation much more better versus me just showing you the encrypted packets and making it all the more confusing. So let me remove the decryption part, apply, and now if you notice, we are not even able to figure out that there is an ARP packet simply because we have not decrypted it, right? Anyway, let's go back to our slides and understand the situation better. So here is the case. Now, even though the slide says static IP, the same thing applies to DHCP, as you will notice shortly. So the client sends out the probe request, attacker sends the probe response, they complete the authentication phase and the association phase. After that, the client, depending on if it is static IP address, it will immediately send out the GRAT-R packets. If it is configured for DHCP, it will time out first and then send out the GRAT-R packets announcing its IP address to the rest of the network, right? Now, here is the thing, the attacker cannot see any of these packets right now because they are encrypted, right? Now, what is the Cafe Latte attack? Well, the Cafe Latte attack uses the message modification and replay hypothesis which is there in the intercepting mobile communication. And we actually play a little trick here. So, what we do, if you remember from the previous video, is given an encrypted packet which is there, right? So currently the LLC header and the ARP header together are the encrypted data, and then you have the web ICV. And if you remember, what we had said in the previous video is this data part can be altered with a bit mask, and then we can also patch the ICV accordingly by taking the checksum or the CRC32 checksum of the bit mask and then XORing it with the encrypted web ICV, right? So if you're confused about what all this is, visit the previous video once again. We've done a lot of explanations there about this specific concept. Now I am just concentrating on how I applied this concept to the Cafe Latte attack. So here is what I did. Let's assume, if you kind of look at the previous slide, that the IP address was 5555 is the auto configuration IP address. I know it's not even in the same range, but let's assume for the second that this is the IP address the client has gotten. Now here is what will happen in a Gratar packet. Basically, you would have multiple fields, and what we are concerned with is that the ARP header itself consists of typically 4 fields, important fields. There are others as well, but we are not bothered. The sender MAC address, sender IP, target MAC and target IP address. Now what we basically want to do is, if we actually can modify basically the sender MAC and the sender IP, then what would happen is this would be converted into an ARP request for the IP address 5.5.5.5. And typically in a Gratar packet, you would have the sender MAC, sender IP, target MAC, most common case is actually all zeros, and the target IP address is once again the same IP address as the host. Now this at times differs from implementation to implementation, as you may notice. So let me get back my packets to show you what it is here. So let me go to 802.11. Let me enable the decryption, apply, and let me just look at the Gratar packets which are here, right? And what we will notice is that the sender MAC is of the client, sender IP address is of the client, target IP address is all zeros as expected, and target IP address is the same IP address as this one. So if you notice, actually the opcode for a Gratarp is a request. Basically, Gratarp is a way by which it's announcing to the rest of the network that this is an IP address which I'm planning to take for my entire network, for my interface, and if anybody has an objection, then they can probably raise that objection right now, right? And here is the interesting thing. What we only want to do is what would happen if we changed the sender MAC address and IP address. So note, if the sender MAC address was, let's say, all A's and the sender IP address was 169.254.41.23, then you notice that this packet is actually changed into an ARP request packet for the IP address 169.254.41.255, and what this means is the client would think someone is requesting its MAC address over ARP, and it would go ahead and reply to that ARP request. So referring to the slides, this modification by going ahead and XORing the encrypted packet with this bit mask, right? Now if you may ask me why this bit mask, were very simple. We really don't care what we change in the MAC address, right? Because any change in the MAC address is a new MAC address. And what we do is we just go ahead and change the least significant byte by XORing it with some value. And what happens because of this is actually the least significant byte of the IP address changes, and this becomes 5.5.250, which typically is in the same subnet. And hence the original gratuitous ARP packet changes into an ARP request packet sent by 555.250 for 5555, right? And hence the victim ends up responding to this by saying, well, 555, that's me, and this is my MAC address. And basically what happens next, I think all of you are already probably guessing, and that is the attacker just keeps resending these bit flipped packets, which end up becoming ARP request packets for the victim, and the victim keeps responding. And basically the attacker starts collecting all of these packets which have been encrypted with the network key, which the victim has stored in its cache. And this is a quick dump of how this would look like once it is decrypted. Tons of ARP requests and ARP responses. And finally, once you have enough of these you've collected, you can run aircrack and go ahead and crack the web key, right? So I had demonstrated this in TourCon, and that's why I had kind of named the key TourCon -- demo. And if you can see, this is a very old version of aircrack, simply because this attack was disclosed in 2007, and that's been quite some time. So now let's move on to actually demonstrating this attack with the tools available. So let me go back to the VM, and what we'll do is let's restart the sniffing. Let's go back here, kill this, and if you actually look at Airbase NG, it has an option to start the Cafe Latte attack, which is basically using -L, right? So the -L option allows you to actually run the Cafe Latte attack. Now, one of the other options we need to use is also the -X to rate limit the number of packets per second. Now, I tried this attack before this video, and there seems to be some problems which I'll discuss shortly. One is, because we are running this inside a VM and we have this external USB card, if the number of packets per second is very high, what happens is the guest operating system tends to use the USB I/O quite a lot, and this actually brings down the overall performance, and we almost see that the VM comes to a position where it almost hangs because of lack of CPU cycles, right? I'm sure this will not happen when you use a dedicated machine on which Backtrack is running. So because of that, we will rate limit this. Try it on your own, you will kind of conclude the same thing. So -L is for Cafe Latte and -X to rate limit it. Of course, if we rate limit, then the number of responses we will get will also be very few, which would mean we'll take a longer time. But I just want to demonstrate the whole logic, and you can complete the attack. So we've started the process of actually waiting for the client, which is currently sleeping. And now what I'm going to do is I'm also going to use arrow dump to store all these packets somewhere. I think I can give it the ESSID PON_me mon0 interface, and basically Cafe Latte demo. Oops. I forget if it even has this option. Hold on. The Aircrack NG suite of tools is so large that you end up forgetting the different options. So I guess it just has a BSSID option. Well, no problem. I guess we could just go ahead and sniff and don't really have to worry about the ESSID for the time being, or the BSSID. There's hardly any access points running there. Right, so this is what we can see, and if you notice, we can see our web access point right here on the top, right? And now what we are going to do is let's start and launch the Cafe Latte attack. Basically, we will go ahead and start our client, right? The client is all started and connected, and shortly it should send out the gratar packet, and you will notice here that airbase ng says that the attack has actually begun. One of the other ways also to figure it out is to look at the number of data packets, which we now see is increasing over time, right? So if you notice, a good amount of data packets are slowly being collected. The number of packets per second, the more it is, the better it would be, simply because you would actually find a lot more packets coming in. Now, what I've seen is, because we are using the VM, a lot of times the entire thing also freezes, right? So I would actually recommend, don't use the VM if you can, use something else. And number of packets are increasing a bit abruptly at times, but over time you would actually end up getting enough packets. So what is happening in the background is what is kind of important. So as we see, the tool is actually sending ARP requests for the IP address of the client, which we can very easily verify, right? This is the auto configuration IP address which the client got, 169 254.41.255, and basically Airbase NG has done the exact thing of bit flipping the IP addresses. Now in the original attack I had just bit flipped the LSB just to ensure that it is in the same IP address range, but it looks like Airbase NG is actually randomizing the entire IP address range as well, right? One of the other things is that the subnet mask is 255.255.255.0, right? So this is how the access point, the client would figure out whether it can even reply to a specific response or not. Anyway, so the whole idea is that once it receives all of these ARP requests, it would end up sending ARP responses. But we can see that the client is a bit slow in its responses. So let me actually go ahead and add a filter to check how many responses are actually being sent. So here is the opcode for request, and let me actually say, well, I'm not interested in requests. There's a ton of frames, so that's taking a good amount of time to filter, right? And now we are able to see all the responses. So ideally what you would want to do is you would want to speed up the entire process by increasing the number of packets per second, and once you do that you would get a lot more packets, right? And one of the important things which we need to figure out here is that each of these packets actually is with a different initialization vector, as you can clearly see, right? Kind of see this counter here, which actually means they are encrypted with the same web key, but they are different data packets. And as you know, a couple of thousand of these packets and the web key will be eventually cracked, right? I leave that as an exercise to you. Word of caution is, if you do not limit this, you may actually find that your VM will freeze, and that's something I can show you here right now in a second. So now let me just go ahead and quickly reconnect once again. And once the connection happens and the attack starts, you would actually find the VM would end up slowing up quite a lot. So right now the number of packets per second is quite less, and that's why you hardly see any responses. And let's just wait for the attack to start. Okay, now it says the attack has started, and you will notice that the packets are now increasing much more faster, right, as expected. And this is a decent rate, to be honest, for something as small as the iPhone. But over time, when you start running this, the whole thing starts freezing. I mean, the luck is that right now it isn't, but I'm warning you. I've tried this attack on this and there are issues. Anyway, so I'm not going to go through the whole script kiddie stuff of saving the packet and then running aircrack, right? If you want to complete it, complete the demo. The whole concept-wise thing should be extremely clear to you at this point, that the tool is taking an ARP, Gratuitous ARP packet, bit flipping it using the message modification vulnerability, which was theoretically talked about a long time back, and then injecting it as an ARP request for the client. Once this happens, the client replies back with an ARP response, which is a new data packet encrypted with the old key. the web key. And once that happens, well, you're going to be collecting a lot of these packets and eventually end up cracking the key. So let me come back to the slides. Now, this is a quick analysis I had done at that time for the version of AirCrack. And on an average, it takes around 6 minutes at maximum speed, which would probably be a little bit over than, around 200 to 300 packets per second, to probably go ahead and crack the web key, right? Now, problems and issues. Couple of times I found the VM hung because of I/O problems, where you're kind of utilizing the USB so much by sending these packets that there are issues. So better to use on a real machine. At times, AirCrack NG was also failing, not working properly as required. I need to investigate on that further. I've already sent a mail to the AirCrack NG team, my friend Rick Farina, Zero Chaos, and I've also told him to talk to Mr. X, who's the author, who had also met during DEF CON. Let's see. So hopefully, they probably fix the issue, or else I'll just come up with a new tool, because end of the day, this is an attack I discovered, so it's pretty close to my heart, right? So I'll come up with one of the original tools. I had written a tool, a proof of concept, tried searching for it in my old archives, but unfortunately I don't have it. One of the videos I wanted to propose is on SecurityTube is video 122, which actually talks about a quick demo of the Cafe Latte on the iPhone. This also has a quick video of me demonstrating the Cafe Latte attack on CBS 5. And here is the original 5-minute clip, or I think 2-minute clip, of me speaking at TourCon.
The configurations. So we decided to move and try
this was the actual
solution.
TourCon demo.
So let's pick up the
Here is my shameless self-promotion.
What happens here is, once again, we go ahead and finish the entire.
Right. So have a look if you have the time. And well, that's it for the Cafe Latte attack. Try it out. It's an interesting attack, and hopefully you will enjoy it. Right. So thank you for watching. Like always, I really love reading your comments. It encourages me like anything to make videos. And as promised, this mega primer, I'm really going to finish off a ton of more videos starting tonight. So stay tuned, keep watching. Thank you.